Hey everyone, so today we're going to be working on notes for the intermediate value theorem. So, general idea of the intermediate value theorem is something that's kind of like this. If I were to be climbing a mountain and I started at 1,000 feet elevation and ended at 5,000 feet, and I asked you this question, I said, okay, was there some time, maybe I hiked for an hour, I don't know, that might be pretty quick here, that I was at 2,753 feet? Was there some point in time that I had to be there? I mean, yes, right? Because if I were to climb up this mountain, it's not like I skipped over it, flew up here. There was some point when I hit 2,753. I don't know what time it was at, but at some point. And then I went to the top of that mountain. So intermediate value theorem is kind of like what it sounds. Intermediate meaning between. And we're looking for a way to prove that some value in between two function values or y values exists. So let's scan down here and talk about the calculus definition we're going to be using. So if f is continuous, this is really important because we can't just talk about any old function. It has to specifically be continuous so that those values will be guaranteed to exist, okay, on some closed interval of a to b. That's just x values. There's some number k, which in this case is kind of like 2753. That's between 1,000 and 5,000, or between those y values. That means there has to be some point or some x value or some c that's between, the time I started and ended, such that f of c equals k, or such that there was some point when I was at 2753. So simply put here, if f is continuous on these x values, then it takes on every single value between f of a and f of b, meaning every single value between 1,000 and 5,000 at some point I hit. Okay, so if you take a look at a graph, here's what I'm kind of talking about. So between a and b, if I started at f of a, okay, we could say this is a value of 1, went to f of b, let's say this is 5, okay, and I asked you, is there some point where I hit this value of 3.5, okay? Well, as I scan here, since this is continuous, there is some point when maybe I hit 3.5, and it's not even a maybe, it's a guaranteed because it's continuous. Now, the graph could have gone straight 1 to 5, and still you would hit a point. It could have gone down, up, above, that way, and maybe at two different points it hit 3.5. But kind of no matter what, there's at least one value where that happened. Now, we used to use this for Algebra 2. I don't know if you guys remember talking about the IVT, and we used to talk about how we could prove a root existed, or a zero. So we're going to talk about that in a little bit. Let's take a look at this example. Okay, I'll pose you kind of a question here. So if I said on 0 to 2, now these are just x values. On 0 to 2, must it be true, kind of rhymes, that f of x is equal to 5.3 for some x value between 0 and 2. So I want you guys to look at this graph. The table also works. So between the x values of 0 to 2, okay, x value of 0 starts here, and x value of 2 is here. So there's my two values. At some point in this journey on my graph from 0 to 2, again, x values, did I hit a y value or a function value of 5.3? Yeah, I did, right? It was somewhere maybe around here. So how could I show that with just a table? Well, take a look, guys. We started at 9. We ended at negative 15. Okay, is 5.3 in between those points? Yeah, right? 5.3 happens at some point, maybe more than once, but at least once between 9 and negative 15. So this is a yes, because we're guaranteed to hit 5.3. Since 5.3 is between negative 15 and 9, then at some point between 0 and 2, I don't know what the x value is, but some value here has f of x equals 5.3. Okay, so let's go look at some of these kind of more formal examples. These could be on a free response for an AP exam, so we had to make sure we're okay with that justification, or it could be part of a multiple choice. So given this function, x cubed minus 5x squared plus 8x minus 9, okay, this is a cubic function. We know it's continuous just because it's a polynomial that we've seen before. It looks something like that. I mean, we don't need to know what it looks like, except we definitely need to know it's continuous. is there some value c between 0 and 5? So again, that means x value here, such that if I plugged it in, I would get back 27. Am I guaranteed? If so, justify. Okay, so here's the process. Kind of like we figured out this 9 and negative 15 thing. I'm going to do the same thing here. So what's g of 0 and what's g of 5? Okay, I'm going to plug in 0 to this. So 0 cubed minus 5 times 0 plus 8 times 0 minus 9. So I get negative 9. If I plug in 5 cubed minus 5 times 5 squared plus 8 times 5 minus 9. I'll do the work for you there. It's 31. Okay, so again, your question here was, can I find function values for 0 and 5 so that 27's in between them? Okay, and I was given 0 and 5. Is 27 in between these? Yeah, right? 31's bigger than 27, negative 9 smaller. So 27 at some point occurred in this interval. Okay, so here's what we're going to say for that justification. Since g of x is continuous, that's the first thing we have to mention, and 27 is between g of 0, which was negative 9, and g of 5, which was 31, by the intermediate value theorem, by the IVT, there exists some x value, or we could say some c value here, between 0 and 5, such that g of c is equal to 27. Okay, maybe we should change this. There exists some c value. Okay, so again, what happened here? Don't be bogged down by the words. Since g of x is continuous, that was important. 27's in between negative 9 and 31. Okay, by the intermediate value theorem, which I'd recommend writing it out on the AP exam, but we can abbreviate for now. There exists some c value, basically an x value, between 0 and 5, such that we're going to get back 27. Okay, the reason that people struggle with this, honestly, is it has a bunch of words. People get overwhelmed and they don't know what to write. So just take a second and read that again. Just think through the process. It's not going to change there in terms of how you're going to justify. So we're going to try a couple more and hopefully you'll get more comfortable with these. So take a look at the next page here. We're talking about a car traveling on a straight track. By the way, if you don't have this page, make sure to insert it into your notes from Schoology. Sorry about that. It says the car's velocity is continuous, so that's important, okay, and the table is below. So I have at 0, we are going negative 20 feet per second. Okay, we're talking directional too, so maybe going left or right or up or down, depending on, we don't actually know in this case, but traveling to the left at negative 20, negative 30, negative 20, negative 14, right? And we're looking from 0 to 60 here, okay? And then you'll notice I'm starting to travel to the right or maybe up, depending on the directions at 60 seconds. So we're going to do so much more velocity, position, and acceleration. So please don't worry too much about these in terms of like wording here. But I do want to do, part B is going to be that intermediate value theorem. Part A is kind of just a preview to what's going to come, which is talking about average acceleration. Okay, average acceleration we can find out by taking the velocity, okay, the change of velocity, so delta, if that's okay, for change, divided by the change in time. Because this would be feet per second, which is actually feet per second squared, which hopefully you guys have an idea that would be a unit of acceleration. So all we're going to do here is basically find that rate of change. Again, I'm going to talk about this more on the next video, but the rate of change for for acceleration, which we're going to find v of 50. Again, we're doing 15 to 50 minus v of 15. How did that change? And then the time, 50 minus 15. Okay, and just refer to our table. V of 50 is 0. V of 15 is negative 30. And then 50 minus 15 is 35. So 30 divided by 35, we end up with 6/7 feet per second squared was our average acceleration. Okay, so again, don't worry too much about that one. Just wanted to give you a little preview there for what we're going to be looking at coming up with velocity acceleration. The bigger issue here is letter B, between 35 and 50. So I'll switch colors here. Between 35 and 50, notice those are my two x values here. Okay. Was there a time when the velocity was equal to -5? So I want you guys to look here, right? At 36, 37, 38, 39. We don't know what happened, but we know we started at -10 and we got to 0. So think if you guys were driving, to the nearest target, okay? And you started at 0 miles per hour. You're chilling in your driveway. Then you end up, at some point you look down and you're going 30 miles per hour. Okay, that means at some point, if I asked you the question, I said, hey, at any point in your trip, did you end up going 15 miles per hour? You'd have to say yes, right? Because even if you went from 0 to 30, the way to get there is you had to accelerate, right? The velocity increased and you got to 15 at some point, but then you ended up at 30. So that's really what this is saying. It's saying, okay, we're at -10. Now we're at 0. Was there some point I was at -5 feet per second? And hopefully you'd say yes. Why is that true? Well, V of 35 was -10. V of 50 is 0. Okay, and then we kind of, again, go with that intermediate value theorem statement here. So justify. Since velocity is continuous, V of t is continuous, and -5 is between V of 35, which was -10, and V of 50, which is 0, by the IVT, or intermediate value theorem, there exists some t value, or some time, right? We don't know exactly when it was, but some t between 35 and 50, such that the velocity was -5, such that V of t was equal to -5. Okay, so again, since -5 is between -10 and 0, there was some time t between 35 and 50. Maybe it was at 40 seconds, 42 seconds, such that the velocity was -5. Okay, and we're going to finish up the last example there. Pause if you need to continue writing your justification. Okay, last example, it says let f be a continuous function, and f of 2 equals 5, f of 5 equals 2. And then it gives us this function h of x, which is f of x, continuous, right? And x, that's also continuous, right? That's just a line. If you are composed of two continuous functions, okay, we know that h of x is also continuous. So that's an algebra fact we know. If we compose two continuous functions, the final function is also continuous in this way. So if we subtract. So anyways, does f have at least 1 0? Okay, what does 1 0 mean? 1 0 really just means at some, oh, I'm sorry, this should say h. Does h have at least 1 0? That really just means, is h of x equal to 0 at some point between 2 and 5? If so, justify. Okay, so let's finish strong here. So we want to know between 2 and 5, what's happening with h of x? And is 0 in between, right? That's all we're really wondering. Is 0 in between the two y values? Because then we can guarantee at some point h of x is going to be 0. So let's figure this out here. H of 2, again, the function here is f of x minus x. So f of 2 minus 2. H of 5 would be f of 5 minus 5. Okay, we're given this information here. F of 2 is 5 minus 2, which is 3. F of 5 is 2 minus 5, which is -3. Okay, and I want you again to take a look. Is 0 in between? That's really what you're wondering. Yeah, it is, right? So good news here is that it's a yes. Okay, and notice it says, does it have a 0? So we should probably answer correctly here, which would be yes. Why? Well, since h of x is continuous, and 0 is between h of 2, which is 3, and h of 5, which is -3, by the IVT, there exists some x value between 2 and 5 such that h of x is 0. All right, that's about it, guys. Thanks for working on that. Thanks for watching, and please bring in any questions tomorrow.